Can you see my screen?
Yes.
Looks good?
Good.
Okay. So thank you, Baohong, for your kind introduction. Good morning, good afternoon, and good evening, everyone. My name is Binbin Ying, a PhD student from McGill University, and currently I'm doing my exchange study at the University of Toronto. And thank you, Baohong, for your kind invitation. It's my honor to present my work after so many wonderful speakers. My today's topic is related to hydrogel ionic skin. So as we know, currently wearable electronics have shown a huge potential for application scenarios, including personalized healthcare, for implantable monitoring, for gait measurement, and also for softer prosthetic sensing. However, current electronics are usually rigid and brittle, and they are mainly relying on electrons to transfer signals. And while our human bodies are soft and use ions for signal transmission. So the mechanical and electrical mismatch usually leads to several potential issues, like the long-term wearing uncomfortability, the tendency to be of inflammation, and the large interface impedance and the low signal to noise ratio is another issue. And also the conventional electronics usually bring a large surface constraint to the surface. So a soft, stretchable, and even biocompatible electronic device is needed in this application scenario. Currently, soft materials such as hydrogels have many unique advantages that can potentially bridge the gap between human bodies and the devices, like the interface between brain and the EEG device, and also the pacemaker between the pacemaker and the heart. For example, ionic hydrogels has many unique features. Like hydrogel is usually wet and soft. They can be stretchable, and their mechanical performance properties can be tunable. Like their toughness can be changed by just changing the cross-linking density, and also ionic hydrogel is based on ion conduction, and hydrogel can usually respond to various external stimuli like light, pH, humidity, temperature, and even a mechanical strain. And most hydrogel is usually biocompatible. So based on this above mentioned features, for wearable electronics, ionic hydrogel has many potential advantages. For example, they can be comfortable to be weared, and they have less inflammation and less interface impedance and high signal to noise ratio, and they are believed to have less constraint to the surface. This slide shows a typical hydrogel ionic skin. And use this ionic skin as an epidermal touch panel for human-machine interaction. They can just touch the touch panel to control the movement of an angry bird, and this touch panel can sense the location of touch and also its force magnitude, which mimic our human skin. So while the development of ionic hydrogel or hydrogel-based ionic skin are still in the infant stage, there are many challenges to be overcome. Here I list several important points that should be addressed to make this technology more practical. First of all, hydrogels consist a large portion of water, as you know, which is not stable for long-term open air usage. Another issue is most hydrogel-based skin-like device is monofunction, while our human skin is multifunctional, and our human skin can sense multiple stimuli simultaneously. Like they can sense the temperature, the pain, and the pressure and the strain at the same time. In addition, the high power consumption, which is also a common issue existing in the conventional electronics device. As traditional electronic signals readouts, such as resistance and capacitance, they rely on the continuous power supply, so which is very power consumptive. So in this project, we developed an artificial ionic skin, or here I termed as AI skin, with multimodal sensation. And this AI skin is multifunctional, is ambient-stable, and can reduce the power consumption potentially. So we got inspiration from our human skin. As you know, our human skin can resist physical damage. They can withstand large deformation. And secondly, there's a lot of hygroscopic substance within the human skin. So our human skin can control the transepidermal water exchange to reduce the evaporation of water. Another feature of the human skin is within the neuron cell, as we know, the ions can move directionally outside of the neural membrane and the inside of the membrane. Like this figure shows the directional movement of sodium ions, which leads to the propagation of the action potential. So we designed our AI skin as shown in this schematic figure. The AI skin consists of 2 layers of tough double network hydrogel, which can sustain large deformation. The top layer of the double network is doped by positive charged polyelectrolyte, and the bottom layer, the blue one, is doped by negative polyelectrolyte. Once those 2 layers were stacked, the free ions of the polyelectrolyte can move across the interface due to the ion concentration gradient. And this step continues until equilibrium. While the polyelectrolyte long chain was constrained by the double network structure. So the hydrogel interface here is what we call the Pelagian zone, just like the traditional electrical diode, and shown in this figure between 2 dashed lines. So after synthesis, part of the water in the AI skin was exchanged with the hygroscopic reagent to make the AI skin, to make this device ambient-stable. So after that, we began to characterize our AI skin. As you can see, our device is highly transparent. The transmittance of the AI skin is over 80%, which is beneficial for the integration of further optical applications. And for the mechanical performance, here we take the strain stress curve as the example. We found that the AI skin can be stretched more than 400 of the original length, and which is way beyond the maximum strain of our human being. And due to the unique bilayered structure mentioned before, the current voltage curve of our AI skin is asymmetric, which behaves like a semiconducting diode, as shown here. and he has a rectifying effect. And due to the incorporation of hygroscopic material, our AI skin have a very good ambient stability. Here I take the stability of the rectification ratio as an example. As you can see from this figure, the rectification ratio can keep for at least can keep stable for at least 1 week. So as we mentioned, it's multifunctional. So potentially utilize the wearable string sensor. We studied the electrical performance of AI skin under deformation. Of AI skin can monitor the change of deformation by resistance, by capacitance, by open circuit voltage, or termed as OCV here, and the short circuit current, or termed as SCC here. So those four signal sensation is what we call multimodal sensation. In addition, the OCV signal and the SCC signal are self-powering or self-generating signals. Here I will mainly explain how OCV works. As shown in this video, due to the existing of depletion zone, the AI skin present a building potential, or here we call OCV, even without any deformation. So when loading the string, the geometry of the whole device changed. So the depletion zone geometry changes as well. And during this process, the ion flows happened in the interface to reach a new equivalent status and leading to the change of OCV. And when unloading the stress, the OCV will recover to the initial status automatically. So based on that mechanism we explained, we found that the OCV correlated well to the applied string linearly. So this electrical performance can be used for self-powering string sensing in the future. And potentially as a skin-like multifunctional sensor, we also need to characterize the electrical performance of our AI skin under other external stimuli. Here we use humidity sensing as an example. Similarly, we found that our AI skin can monitor the change of humidity, by the resistance signal and also the self-powering SCC signal. And we found that those signals correlate well with the humidity at different string levels. So okay, now we know our AI skin can do humidity sensing, can do string sensing. So we demonstrate our AI skin for wearable string and humidity sensors. And from this line, we can see that the wearable string sensor can work well at different humidity conditions with multimodal signals, including the signal of resistance, the signal of capacitance change, and also, as shown in this video, the OCV for self-powering sensing. And for wearable humidity sensor, we use our AI skin to monitor our human breath. As you can see from this figure, our AI skin show a relatively repeatable performance to monitor the humidity levels of our breath, and the performance, like the responding time and also the recovering time, is comparable to some commercial humidity sensors. So then we construct an AI skin array by the integration of 4 ionic diodes. So basically by simple pressing the ionic diode buttons, we can use the self-powering OCV signal to control the movement of a greedy snake, which means our AI skin can be potentially used for human-machine interface with less power consumption. And finally, we also demonstrate our AI skin for mechanical working energy harvesting. And this is the SCC and OCV signals during human working by just one layer of the AI skin device. And in the future, we can stack multiple layers of AI skin to increase the output of the power to make this technology more practical. So to conclude, in this project, we designed and developed an artificial ionic skin using hydrogel with superior mechanical properties. They have very large stretchability, and this artificial hydrogel skin is multimodal, can do multimodal sensation. They can transduce the mechanical and the chemical triggers into 4 types of signals. And this AI skin is multifunctional. They can sense force, strain, and humidity simultaneously. And due to the incorporation of hygroscopic material, our AI skin is ambient-stable. They can work in a wide range of relative humidity condition. And for application, we demonstrate our AI skin for wearable string humidity sensing, for human-machine interaction, and energy harvesting. And I believe these features of our AI skin can potentially blur the boundary between humans and the device, and promise broaden usage ranging from wearable and implantable device for human-machine interaction, for intelligent software robotics, and also to for personalized healthcare monitoring. Finally, I'd like to thank my supervisor, Professor Xingyu Liu at the University of Toronto, and my co-supervisor, Professor Jianyu Li from McGill University, and also the lab mates from biomedical microsystem lab, and also the lab mates from the lab of biomaterials engineering. Also, I'd like to acknowledge the funding source from McGill University, McGill Engineering and Doctoral Awards, and also NSERC Awards, and also the funding source from University of Toronto. So thank you for your attention, and any question is welcome to be raised here. And you can also follow me on my Twitter, and more information about today's talk can be referred in my recent publication on materials horizons. Yeah.
Okay, thank you, Binbin. Jingjie has a question.
Cool.
Hi, can you hear me?
Yeah.
Oh, hi. Yeah, hi, Binbin. Thank you for the wonderful talk. I have a question for your, I think that's a unnotched tensile test. Maybe on like the page 12, there was a video. So I was just wondering, I see that you mentioned about this kind of, it didn't go to like fracture for certain elongation, but I noticed like on the right side, there was maybe the crack initiation. I was wondering if that's intentional.
Oh, you mean this circle?
No, the next one. Yeah, the video.
The video, right?
Yeah, so I was wondering if that was like you intentionally introduce something, or
no, we don't do it intentionally. It's
okay.
Just automatically, and I think it's the uniformity issue of the hydrogel during fabrication.
Oh, I see. Yeah. Okay. Thank you. I was about to ask if you think it's the heterogeneity of the material.
Yeah. That's a common issue actually in the hydrogel.
Oh, okay. Yeah. I see. Yeah. Thank you. Thank you for the clarification.
Thank you.
We have another question from Tirapali.
Hello, sir. Am I audible?
Hi.
Am I audible?
Sorry?
Hello.
Hi. Yeah. I can hear you.
Sir, very good presentation.
Thank you.
Very good work. I have one doubt. How did you manufacture this hydrogel shape by additive manufacturing technique?
Sorry, can you repeat again? Because I found the sound is a little bit light.
Okay. How did you manufacture this hydrogel shape?
Shape? You mean can I rephrase your question? You ask me how to shape the hydrogel, right?
Yeah. How did you manufacture this?
Okay. How I manufacture the hydrogel,
Yes.
right? Oh, it's actually it's a two-step manufacturing protocol. The first step is we synthesize the first network. Or here we use we use agarose as the first network, but just by simply heating to a certain temperature, and the hydrogel will melt, and then we pour the whole material into
Okay.
and the hydrogel will be shaped, and then we soak the whole device into the second network. Here we use PAAM, polyaquamide solution, and then we use UV to cross-link the second network hydrogel. Then the whole device can be stacked.
Hello. Okay, sir. Thank you. We can manufacture by
Yeah.
We can manufacture by additive manufacturing also, right? 3D printing. It's hydrogel is a 4D printing material, right?
Yeah, you mentioned can our hydrogel be 3D printable, right?
Yes.
Yeah,
That is my question.
I think so. Although currently I'm not working on this area, but I know some of my lab mates are working on 3D printing of this material to integrate the multiple device on a single sensor array.
Okay.
Yeah, I think it's doable.
Yes, sir. Thank you very much. Thank you very much, sir.
Thank you for your question.
Okay, next question from Hedwig Banerjee.
Hello.
Hello?
Yeah, you can hear me, right?
Yeah, very clear.
Hi, Binbin. So it was a fantastic talk, actually. I really like your AI skin, and I have gone through your publication as well, especially the materials one.
Oh, thank you.
So my question is actually down the line of the notch, right? You have a puncture of when you are doing the tensile testing, which is like uniaxial testing machine, and you have the fracture. And do you have ever thought of like to see a kind of analytical modeling to have a kind of a mathematical outlook of the strain energy density function and how the notch or the fracture moves from one to another if we go beyond 400%? So did you think about that? So I'm a bit curious about the energy domain, how it will play. Yeah.
Okay. Actually, this is a very good question, and I can tell you that we in this project we only do the experimental test. We haven't done any analytical analysis because I am not a theoretical guy. So, yeah. But I know in my lab, in my co-supervisor's lab, they are some people are very good at theoretical analysis. They are doing a similar kind of work. But personally speaking, I'm not good at the analytical.
Sure. Thank you very much, Binbin.
Thank you.
Jing, you have a question?
Yes, I have one question. Wonderful talk, Binbin.
Hi, Jing.
So
Thank
I'm
you.
just wondering whether if you, like, for example, attach this hydrogel like AI skin to the real skin, and the skin like sweats and gets on like body fluids, so they have ions as well.
Yeah. And
change the ionic status of this bilayer, and would that change this the mechanical deformation for this AI skin?
for mechanical, so your question is whether the ions in our sweat will have an impact on the mechanical performance of our AI skin, right?
Yes.
So firstly, let me clarify that we haven't done any in situ or in vivo test on our AI skin directly, but according to my experimental experience, the ions won't cause much big difference, big impact to the mechanical performance, but probably they will induce some little disturbance to the electrical performance, because our AI skin is like a diode. So I guess I hypothesize that according to my previous literature reading, the external ions will cause some little electrical disturbance to the electrical performance.
I see. Thank you. Yeah, I'm just wondering if you can
good,
use this as
very
like biomedical applications for that.
Yeah.
That's very good. Thank you.
Transmission of the electrical signal will be much quick than the diffusivity of the ions at this interface when you have a sweat. I don't think that will affect too much.
Yeah, I think Paul, you also working on the similar work published on Science, right? So you maybe also can give us some advice on.
I will save time to the discussion.
Yeah, we can discuss later.
If we don't have any other questions, let's thank our speaker, Binbin, and we move to the next speaker. Thank you, Binbin.
Thank you, Bao.